Hey everybody, Blake Veneer here again with another part in my series about space-time particles, which is um, covering an Aether model that we can use to address some of the unresolved issues in physics, such as dark matter. In this particular episode, we are going to be looking at frame dragging and digging into some of the reasons that Aether models were shot down in the past. So we're going to look at the Michelson-Morley experiment again, and just this is the Aether wind. Then we're going to look at the Michelson-Gale-Pearson, which is the rotation, and then from there we're just going to look at parallax and stellar aberration in Aether models and how that would work. So the first part is Michelson-Morley experiment, which was an experiment meant to measure the Aether wind. I already covered this once, so I will be kind of quick here. But essentially, the Michelson-Morley experiment was an interferometer where we would bounce light off of mirrors here, another mirror here, and then there'd be some sort of fringe pattern on the output. That's supposed to be a sine wave or something. You're really looking at a fringe, so it'd be more like fringes like this, but whatever. So, but essentially some sort of periodic output, and this was put on a giant mercury like a float, and it could, it was on a giant table, and that was on a piece of like a mercury bath, so that you could rotate this giant apparatus pretty freely. And the thought was, if there was an Aether wind, you would see this fringe pattern change based off of the angle of this apparatus relative to the Aether wind. And again, this was a null. So, a null result, which implies that we have some sort of and so what would that look like? So before, we talked about how we needed to create something called an inertial sphere in order to get around Newton's first law, which is anything in motion should stay in motion. And if we have everything moving through some sort of medium, we need to create a way to not transfer momentum to the medium. So we would create this inertial sphere. And so if there's an inertial sphere around Earth, so here's Earth, boy, not to be confused with an electron, and Earth is moving this way, then around Earth is going to be an inertial sphere, and everything here, so this is, right, so any little piece of space-time or space-time particles, in any one of these volumes, maybe they should be circles, but basically all of this inertial sphere is going to have the same V. Whereas V out here could be 0. Right, and so this inertial sphere is going to have the same velocity as Earth. So if all of space-time or all the space-time particles around the Earth are traveling with Earth, we would expect no Aether wind. Okay, great. So that's pretty easy. Inertial spheres basically explains why we don't measure an Aether wind, and explains how we are dragging, the space-time particles around us with us. However, the next argument is, if we are dragging space-time particles with us, then we should also drag space-time particles with the rotation of the Earth. And so then that goes to the next part. So the next part was where the Michelson-Gale-Pearson experiment, and that was try to measure dragging of the aether or the spacetime particles due to the rotation of Earth. So essentially, that we had a ring interferometer, which is basically light comes in this way, it travels around a path here, mirrors, 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 but also it has a beam splitter which creates light going in the opposite direction. Maybe there should be. And then the output is again some sort of interference pattern. Right, so the path length of the light varies based off the rotation of the instrument. And if we make a large one of these, put it on the surface of the Earth, we should be able to see, well, we would measure rotation of the Earth, assuming that there isn't any aether dragging. And that's what basically they measured. So or at least it does not. Right, so because we were able to measure the rotation of the Earth using this instrument, and we did this very well, they can agree to astronomical predictions. We can assume that the Aether is not dragged due to the rotation of the Earth. So, in order to make sense of this, because now they're kind of two different, Michelson-Morley experiment says that Aether does get dragged. This says it does not. So we need to look at the two situations independently. So for the Michelson-Morley, the size of the inertial sphere is proportional to the momentum of the object. And the size, when I say size, I'm not necessarily speaking about just purely the radius, but it could be the total volume of space-time particles moving with the object. And that can, we're going to have to look at that more detailed later because we'll have a increase in density due to the increase of velocity, and I'm not sure if exactly the radius is going to increase or if it's going to be perceived to increase from the moving perspective. So anyway, but the point is, the faster an object is moving, the more space-time particles it will drag with it. And so if we look at that, again here, Earth is going this way. We have this sphere. Please work. Now, again, everything is moving in this direction, right? And that's because every bit of Earth is dragging, right? Any point on Earth is going to have the same contribution to the drag of the inertial sphere, right? We all agree. This one feels that direction. Over here, it all agrees here, right? So this large inertial sphere is only created because all of the linear momentum of Earth is dragging it in the same direction. right? And so, like, imagine if you had a small person over here, their inertial sphere is going to be, maybe not that big, but it's going to be the same kind of idea, though. It's around the person, we're going to drag space-time with us. So now let's look at the rotation. So we're going to have a point here, and then I guess we'll just say this direction, right? So this is the Earth. Right. So now if we look at a little volume here, the volume here is going to be dragged by all of this momentum. And you might say, oh, the Earth has a huge angular momentum, and that's very true, but it does not all contribute together to drag the space-time particles around it uniformly, right? So if we look here, the dragging here is going to be related to this large, right? So I should have made so even just in line, we're going to see that the contribution is decreasing as you get further away. The velocity at any of these given points is going to be inversely proportional to the radius. So as you get closer to the center, the velocity decreases. Now we also have an issue over here, is this little spot over here is moving this way. This little spot over here is moving that way. This little spot over here, I don't know why that's so big. Oh dear. Right, so the point here is that these two are both adding to the dragging of that this little square we're interested in, but there's a component that's going to cancel. These are going to perfectly cancel with each other. Oh, geez. And this one is going to cancel with our cancel with the other side. Granted, there is going to be a distance issue, like a relationship, so it might not have that big of effect. But again, the point here is that all of the angular momentum of Earth does not uniformly drag any given spot. So therefore, the Aether dragging is relatively small. And so that would basically explain why we get a null result for the Michelson-Morley, but we get a positive result for Michelson-Gale-Pearson. Now, let's just look at the bending of light, and specifically the bending of light due to motion. If we're here and we have my little laser and it shoots light out this way and it's moving this way, this light is going to take a little bit of time to travel this distance. So this is going to be T0 and at T1. Right, so at T1, the light will reach us. However, we're going to see that light as if it came from its location over here. So now let's do a little experiment where what if we have this laser at an angle? This is probably too extreme, but bear with me. Imagine that shoots light this way, right when we are perfectly in line. T0. And so when this actually hits us, the motion of the laser is going to bend light towards the direction of motion. So we're going to see the light as it appeared at its closest point. However, its actual location is going to be all the way over here. And so that's kind of what the aberration of light. And there's a bunch of equations. So like a typical equation would be cosine. And these get really confusing relative to who's moving and what angles and what. But typical, you'd look at, so the angle of the observer. So in this case, the human would be the observer relative to the angle of the source. Another interesting effect would be the searchlight. So if we have a spaceship that's emitting light all around it, basically the light is going to, from a stationary, from this person's view, the light gets concentrated towards the front, and this is called the searchlight effect. It's also going to get blue shifted in the front in the direction. So anyway, this is basically just, there's a lot of good videos explaining this in more detail. This is probably not the greatest explanation, but this is how it works for a non-Aether universe. So with this in mind, one of the big things against Aether models is this weird parallax or aberration of light argument. And I'm going to try to explain it. I don't really understand the logic, and so therefore if somebody else can explain it better, I'd love to hear more about it. But here I go. If we're on Earth and we have a telescope, it's a very big telescope. But if Earth is moving this way, then in order to see light from a star, we have to angle the telescope in direction of our motion a little bit so that light comes through the apertures and we can see it. And this is similar, I guess, to what I was saying before. Now, they somehow say that if you have Earth moving again, and you have, so maybe we'll just do this. Pretend that we're zooming way in. So the Earth is now a small arc. If you have a telescope and you fill it with water, they're proposing that light is going to come in, would it be at an angle? I don't know. Come in at the same angle, but then if you have a medium here, it is going to drag the light with it in this velocity or in this direction, so you wouldn't have to angle the telescope anymore. And so the same thing with, right? So now if we get rid of the telescope, and we had this like, gosh, let's erase this. Again, I'm sorry, this is so confusing to me. So here's the Earth, not to be confused with an electron. Here's the Aether, our inertial sphere, and they're saying that light would come in, I don't know how. So does it come in at an angle and then go, gosh. And so basically the thought here is that, um, if you're moving this way, the light is going to get fully dragged with the inertial sphere. And so we wouldn't actually measure this angle. And so then if Earth's going this way, you're having the same thing here, inertial sphere, light might come in here, and then it's again. So regardless of the direction of Earth, we would not measure an aberration, a stellar aberration. I think this is their argument. And so what this takes is some crazy, and then I'm also, so in order for this to happen, the density of Aether needs to be very high. And I think somebody like quoted it like in like an unrealistic level of, um, Aether. And also the other issue is, I'm wondering if a lot of these arguments are pre Einstein's relativity. And so nobody's really adapted since, and we keep falling back to these weird explanations. And so I don't even know if they even make any sense anymore to bring it up. But there's that. We're going to look at how light would actually get bent in, a model for space-time particles. And there's two ways. It's one is due to the change in density, and the other is due to motion. So I introduced this concept of conservation of time. And, this is period. I'm trying really hard to make those P's look different. So this is period. Whoops. And so when the density changes, the period of the light also changes, relative to this formula. And so we can do some little, P1, N1. Now, if I want to multiply by, this essentially becomes H over C times frequency 1 over N1 equals. And this is momentum. And this is why I was so concerned about those dang P's. And so we got P1 over N1 equals P2 over N2. So this is now momentum. So we have this relationship between momentum as the density changes. And we can very easily do some of those, kind of Snell's law type analysis. So N1, N2, 2, which is, that's just our normal vector. That should have been a straight line. So this is P1. This is P2. So then here we have theta 1, theta 2. And so this would be px1, py1, py2, px2. So we're going to say as this light comes in, px1 does not, the parallel component relative to the surface is not going to change the momentum. Oh, geez, 2. And so we know with just the trig, P1x equals P1 sine theta, P2x equals P2 sine theta 2, 1. And so we can set these two together, or set these equal. P1 sine theta 1 equals. However, we also have this relationship. Maybe this deserves to be boxed, where P2 is equal to P1 and 2 over N1 from this. P1 we can drop those, and essentially we are stuck with N1, same kind of thing, Snell's law. So that would be the angle deflections due to the change in density. Now let's look at how the aberration of light behaves with an inertial sphere. So here we have an inertial sphere, and I'm going to say this is the rho of inertial sphere. This is rho naught. This is going to be equal to, right? And so basically N is equivalent to gamma in this situation. And so what's interesting here is if we have this inertial sphere, light with different density, light's going to behave weirdly, right? So, boy, that was pretty extreme. I didn't mean to intersect those two right there, but basically light's going to be coming in and bouncing around, and this is going to get hard because there's going to be this considerable deflection of light due to density. And so, right, so now we have to contend with two problems. One is due to, two is Now, one little trick we can do for optics is, let's look at, if we have an eyeball with some sort of optic here, and say we're trying to look at all these trees. I don't know how to draw a tree. Now, imagine we want to see how this image changes with optics, the optic in the way. Well, light is coming from all different directions. And so there's two ways we can do this. One, we can say, well, look at this ray here. Does it enter? We look at all the rays that enter the optic and we only pick the ones that do. That's a lot of work and quite confusing. And so one trick with optics is you say, well, I know I'm only interested in the rays that are hitting my optic here and the rays that are passing within within my optics. And so if we start with our imaging and then we do the ray trace in the reverse direction, we can see which points of the image are actually going to be applicable to the situation. And so we're going to do kind of the same thing for looking at our moving spaceship. Now, if we, again, we have this relative to gamma essentially, equals n. But if we have light moving perfectly radial from the center of this inertial sphere, there's going to be a 90-degree here. And the good thing about moving 90 degrees is no So now what we do is we have purely an angle change due to the velocity. So we're going to hit here, and this is going to be deflected here. Now, here's one of the problems with this, is if we're going fast enough, does it come back? Right? The equation would say that it's going to get pointed in line with the velocity, So at some point, light might try to exit the inertial sphere and then hit back in there. So, or re-enter the inertial sphere. And that doesn't make any sense. So let's look a little bit at what that means. So I did a little easy simulation. And basically, this is our circle. This is our inertial sphere. And I basically had light rays leaving the inertial sphere. And if you look at this green corresponds to, boy, is that green must be somewhere in here. I don't know. And this is equal to 1. Oh, wait, sorry. I'm just going to say the Doppler. Right, so a Doppler shift of 1. So we start with 1. As we move forward, we have a higher Doppler. And then as we move in the back, we have this slight red shift, right? So in the front, we have purple, which is going to be a Doppler, a blue shift. In the rear, we're going to have the red shift. And so at almost 0.1 of the speed of light, we have a very small gamma, no problems. Now we're going a little bit faster, so more of the light is going to be compressed forward. We're getting a Doppler over here of now 4 times a blue shift of from our source, and our red shift is now at, the light coming directly behind is almost shifted to 0.2 of our initial value, and it's still like no problems here. And this is at 0.9 of the speed of light with a gamma 2.2. I guess 2.3 is the closer. Now, even if we go up to 95% of the speed of light, it is right on the edge of not violating any of the concerns with light re-entering the inertial sphere. But if we go faster, we're going to have problems. Now, I went quite a bit faster just to show, but at 90, I guess it'd be 99.9% of the speed of light, we have considerable amount of light being reflected back into the inertial sphere. So this is the sphere here, and this doesn't make any sense. So how we can get around this easily is if we just said the inertial sphere changes shape. So imagine that the inertial sphere changes shape such that the light leaving the inertial sphere is at minimum tangent to the inertial sphere. And so that's essentially, so basically the emission angle becomes the tangent to the inertial sphere so that we don't have it crossing the inertial sphere. And what does that look like? So at point, this is 99.9% of the speed of light, same speed, but now we are basically just making sure that light cannot pass the boundary. And so that's kind of a neat solution. But here's the problem here is now this angle is no longer, I don't know why I did a square. The light here is not equal to 90 degrees. And so my initial idea, having the light leave 90 so that we don't have density effects, is no longer valid. And so what does the angle, how much does this angle affect the light coming out? Well, here's another thing, is I had to back this down to 97% of the speed of light. And you can see that it is, and so here, any light moving this way is not affected, is leaving normal, or any light that is moving in this direction is leaving the inertial sphere perpendicular. So there's no effect due to density. And so we can just disregard all this. But you can see that as we're leaving here, it is getting bent purely due to density. And this is bad because it is a runaway effect, right? So as we increase speed, we need to increase the angle, like the angle to move it forward, right? The aberration of light purely by the velocity, but then we need to account for this larger tilting, this deflection due to density. And we also got a potential issue where light is going to start refracting, bouncing off the inside here if we go faster. So this gets very confusing very quick. And there's one even a bigger problem with this, is that this isn't even the right way of looking at it, because I am assuming this. So this would be, if anybody has any guesses why this is so wrong, give it a shot. But here we go. In order to make sense of this, I'm assuming that there's high gamma here and then gamma here. Or maybe this should be n is greater than 1, n is equal to 1, right? But this doesn't make any sense because the reason why there is gamma in the first place is because I said that in order to move space-time particles around this sphere, we had to increase the density because the velocity of the fluid is limited to the speed of light, right? So here should be, well, maybe we should do this. Black. This area here needs to be gamma 2, or it is not equal to 1, right? So what does that look like? So a more realistic density distribution, and this is just me making some distribution up, but essentially right around the edge, so this is n, or like, I mean, I don't know which one I keep, and then right on the edge is gamma, and then this is, you know, you can look over on this bar on the left side, is that purple is essentially 4, and then as we get further away from the inertial sphere, we're going to approach a gamma of 1. Okay, so now let's look at the path of light due to purely the density change. So this is, we've backed off the velocity. This is 20% of the speed of light at a gamma of 1.02. And here, this is going to be very, you know, there's no apparent bending of light due to this change. So let's speed up a little bit. Now I picked 90% of the speed of light because just for fun, if we look at the photon sphere of a black hole, which is where this is a black hole. Basically, the photon sphere is where light, I talked about it before, but I called it the photosphere, so that was my fault. And that should be a perfect circle. But if light goes, if you shoot light perpendicular to the surface at the photon sphere, you're going to get a perfect orbit. And we're going to call that gamma. So R of gamma, and that's is equal to 3gm over c squared, or it's equal to 3 halves rs, and rs is basically the radius of the Schwarzschild, or it's a Schwarzschild radius. Now, if we look at the time of something very far away relative to the time at a given r, essentially this is our gamma feature, or our gamma equivalent. And this is equivalent to 1 over which can be simplified to that's the Schwarzschild radius again. So now if I'm interested in R of gamma for here, so gamma of gravity is equal to, right, so R is now 3 halves over RS, right? So 1 minus, right, so 3 halves is now 2/3, and so that simplifies to 1 minus 2/3, which is 1/3, which essentially comes down to square root of 3, which is essentially 1.7. For an idea, there's a lot of decimals left out. But anyway, just for an idea, we can cause light to bend so much to orbit a black hole with only a gamma of 1.7. Now, also keep in mind that the bending of light in order to do a circle is relative to, the radius and all this stuff. And so it is not like a perfect relationship of what I'm showing, but just to give an idea that when you're going 90% of light, you have quite a significant gamma and time dilation effect. Now, the problem that I'm trying to point out here is the amount that this light bends is proportional to the the change in density. So if we make this little here sharper, we actually get a different trajectory. Right? So now if you look, we get a much sharper change in density, and that's going to cause the light to even bend further. Now, if we decrease the change in density, the rate of change in density, we have a much mellower escape angle. All this to be said is that we need to do a lot more analysis on this, and I didn't want to spend all. I'm going to basically come back to this problem. So we need to account for, the velocity of space-time particles moving in all around from here, but also we're going to have some sort of density distribution due to the compressing of the space-time particles, and we need to account for how they're moving at the edges and how this vector, so light, it's going to be here, and so if light is moving along a path with a varying velocity vector, that's going to really affect, the output answer here. So here we're going to come back to this, but this is only for really high gamma values or speeds. And so mostly we're going to be interested in our more natural energy levels at the moment, but we'll come back to this. Jeepers. That was a lot of... So future experiments, well, let's just look at how our current measurements would be affected. So this is Earth. If we're moving this way, there's going to be a star out here, and its light is going to travel this way. And in reality, though, because we have moving relative to each other, so because Earth is moving relative to the star, we are going to have a perceived location offset by the theta, our angle theta. And this is going to vary depending on, and so, typically you would measure this with 6 months apart so that we get, 2 different vectors for the velocity. But it's very small. But how does this affect, or how would an inertial sphere affect this measurement? Not a bad circle. So we're expecting light to be this way. However, this is pretty extreme. So I'm arguing that the angle this is going to have the same physics as the normal aberration of light, right? However, the paths between our current theory and inertial sphere or spacetime particle theory is going to be different, because the path here is going to be this one. And so there's going to be D, right? And so D is going to be proportional to the error of our measurement. And so what does that look like? We're going to call that phi or phi, I don't know, and start to do the math here. So the distance over the radius of the inertial sphere is going to be proportional to sine theta. And I'm going to call this distance to the star. It's a t. And so the radius of star t is essentially, because all these values are so large, it's radius of the inertial sphere plus whatever R2 might be. And so d is also equal to radius of the star. Now, one thing is when theta and phi go to 0, when they approach 0, sine theta approaches theta. I'm going to say sine phi is equal to r over st is equal to, we're going to grab this one. So ri sine. I'm just leaving out the. And so now we can use this basically property or identity. Phi is equal to r st over theta. Now to put some, this is r. So to put something in perspective, RST for the closest star is roughly 4 light years. What do we think the inertial sphere around Earth is? The moon, radius of to the moon is 1.3 light seconds. So basically any value here of Ri over RST is going to essentially be 0. So the error here is there, but it's going to be very, very small relative to a small theta already. So I don't know if this would even be apparent. So other experiments, we could have, moving spacecraft. We could try to look at something, if we ever had a really good view of a fast moving object, right? So as I said before, something massive, right? I'd made the argument that special relativity and such is only been used in low momentum situations. So it'd be very interesting to look at a large momentum situation, like something with appreciable mass moving close to the speed of light. And there we would, see some sort of, changing of the light. And so that would be something. And I'm sure there's a lot of other ideas that um, we could do. But if anybody has any other thoughts, I will try to write them down and we can make note of them later. And so that basically sums it up. And so the whole summary here is basically frame dragging is proportional to the momentum in line. And so that's why the Earth can drag the space-time particles around it, but why we don't see rotational momentum dragging our space-time particles. And the other main point is that there's really no major deviations from normal physical experience, right? So like low gamma values, anything that we would expect when we're looking at distant stars. So we really shouldn't expect any large deviations from our current measurements with Aether model or space-time particles model. Now this is kind of my next few things that I want to cover. I might not do this in this particular order, but I want to first look at what we've done so far and see how we can get rid of dark matter, and so how we can solve the rotational curves of the galaxies using flowing space-time particle model. We're also going to try to explain the double slit experiment at some point. I want to talk a little bit more about light. This might not be about space-time particles in general, but I want to talk about kind of what I think is a huge misconception we have. We can also look at faster than light travel. Einstein's equations basically have a giant panic attack when you approach C because you start to get infinities. And I'm going to argue that in a space-time particle model, this is not such a big problem. And it would be, so we'll just spend a little bit of time of doing a hypothetical experiment of what happens if we exceed the speed of light. Now, this one more about frame dragging and special relativity. So basically, I had shown a whole bunch of meandering work that had no relative physical result. And I would like to get back into that, do a more detailed dive of looking at how light will bend around a moving inertial sphere with a correct velocity profile of the space-time particles and with a varying density of space-time particles. And that also my math on how the light will bend with a density change of space-time particles. I just want to make sure that that is looking correct and do a little bit more verification there. And then I want to talk about light and black holes and not really focus on the physics of at the black hole, but just kind of when we're close to the black hole. And then maybe briefly talk about dark energy a little bit, because that's also something that's kind of very crazy in my mind, in terms of adding so much energy to make our world make sense. And then once we kind of do those kind of high level overviews of these topics, I want to start modeling gravity using space-time particles. And remember, we had shown how light bends due to density, but gravity is a force between two, or an acceleration, however you want to look at it, but it's an attraction between two particles of mass. And so we have not even touched on that. And that's where it gets is going to be pretty involved. So that will be kind of a bit down the road. And I just want to get these like easy, kind of exciting topics out of the way first. So thanks for your interest. If you have any comments or questions, please leave them in the comments below, and I will catch up with you all soon.